Nice. Okay, let me just let me see here. Okay. Okay. So first of all, I wanna thank you for the possibility of talking about the work that we are still doing here. I will talk a little bit about lightweight tokens and path tracing, which are basically two main use cases about the token thing that's we are doing. My name is Marques, and I'm a PhD student at Universidade de São Paulo. And our working group is composed. Oh, sorry. Let me just take this Windows thing out of here. Sorry about that. Okay. Yeah, nice. So there are a lot of people working together in this group, and we also have some people from HPA. So thank you everybody that's part of our working team. And basically today I will make a brief introduction and show what are the main objectives that we are looking to attend here. And we'll talk about the nested model scheme is something that we are working here on this project. Also a little bit some information about token path tracing and what are the models that we are trying to make work. And then the last part, the part that we most like, the demonstration, and try to show some interesting things happening here. And that's it. So assertions or claims have long been as a topic of debate here and with the SPIFFE community. So reading all the stuff and taking all the information that a lot of things that communities that have already discussed, we can extract some main needs that we have been working in. Basically, what we need when we talk about this kind of thing is that we need a way, we need a system that allows n workloads to make you authenticated statements. So the idea here is to allow the workloads to create tokens or create assertions and sign it and allow the validation in an easy way through since the origin of any call until the destination of that request, we need to have a way to validate and to create this path. So to do that, we need also a token scheme that allow this kind of support, because we will have distributed signing. So we need to validate this, being aggregating or concatenating the signatures and allowing to make some kind of attenuations. This is a word that we can see in a lot of works that try to do this kind of thing. So to define some minimal structure and to work on this kind of thing, we are analyzing or have analyzed a lot of use cases, that a lot of things that could be could use this token structure. And we have bring here two of the I don't know if they are the main important, but are one of the main important use case here, which is allow a workload to act on behalf of a specific user. Because when we think about SPIFFE and SPIRE, we are just interested in workload identities, but this could be useful to tie some user identity to a workload. For example, you can have a front end that is trying to access the user data. So this workload should have a specific authorization tied to user identification. So this is kind of what we do here. And also we need a way to provide the path of workloads. So we have a call. Let's imagine that request comes from a user, enters in the front end, and then will pass for many workloads until reach its destination. So we need to know for which workloads that pass it, and also to validate each signature that each of these workloads have done. Okay, so let's understand better what is this kind of nested model. Basically, when we think about assertions, we have discussed some models of assertions, but we are trying to simplify at most, at least for this moment. So our assertion here is basically similar to a JOT token, but without the header. We imagine a simpler token than a JOT token. So we just removed the header. And if we need some kind of key information or algorithm, anything like that, in this model, we can put just inside the payload and make a signature. And this is kind of basically assertion. And the point here is this assertion is created by a workload and is passed ahead to another workload. And this another workload can add new assertions to this token. So it just adds a new payload here just before the original assertion, sign everything, and add the new signature here on the as the last part of this token. So if you compare with JOT token, it's quite similar, but JOT token is always composed by 3 parts. And here we don't have this kind of limitation. We can just keep adding parts here to this token because it will be useful in the validation phase to decouple these things and analyze them individually. So that's the way it works. So when we add a new assertion, we just add the payload in the beginning and the signature in the end, and this token keeps going on the path. Okay, and that's another interesting thing that we have thought about when we was talking about token tracing, is that imagine the scenario here. We have an original assertion that was issued by some workload called ID1, and this ID1 workload will pass this token ahead to ID2. So ID1 will need to add this audience claim here inside the payload, pointing to the ID of the next workload. So basically, we are doing here some kind of link between the original assertion and the next one. And when ID2 needs to append new information here, this ID2 will be the issuer. And as the previous step, we will need to add as the audience the ID of the next workload. So issuer will create this payload, will sign it, and will pass ahead to ID3, which basically will do the same. And here we can create, doing this thing here, we can create some kind of chaining. And this chaining is important because it avoids some kind of attacks, for example, trying to remove the last assertion. So imagine that we have this kind of token that is addressed to ID3, but someone takes in the middle of the way and try to remove that last part and use it as a new assertion here. But here doing that, the issuer and audience links here will be broken. And even if the signature is correct, this token should not be accepted, and we avoid this kind of attack. But someone should be interested in remove some middle assertion here. And of course, it should not work because if this guy remove, for example, this red part here, so here the issuer should be ID2 and the audience ID3. But if we remove, we also broke this kind of link. And if the signature is correct, this token should not be accepted also. So this kind of thing here is interesting because we have this kind of chaining and doesn't allow also any modifications in the payloads, in the existing payloads, because if you do that, you will have a valid link here, but of course, the hash of the payload will be different and the signature will fail. And also all subsequent signatures will also fail because changing this, all the next hashes will be different and everything will fail. So that is not possible too. So this kind of construction is interesting to our token path tracing model. But when we think about this, and we have thought about a lot of this kind of thing, we had divided the solution to main models. First one is the ID mode, and in the ID mode we have exactly what we saw in the last slides. We have an identification, which in this case is the SVID. So we will use the SVID to extract and use the private key of this workload to sign the token. And when this workload signs this token, it will send the certificates that are inside the SVID to identify itself and to validate the assertion that was created. So it will grant that the issuer audience link will be also valid. But there are some use cases that this kind of identification of the workload is not necessary. Maybe we don't just need the validation of each step, but we don't need to know the workload identification. So in this scenario, we can use some tricks here, and I will show some of them here about how to concatenate the Schnorr signatures that we are using and achieve smaller tokens and fast verification. So let me talk just first about the ECDSA-SVID, which is our ID mode, and how it's working in our proof of concept. Basically, what we will do is to use the SVID private key to sign the tokens. So let's imagine this flow here. We have our ID1 workload, and this guy here will create a token, sign it with its private key, retrieve it from Spire, and then attach, or better say, not attaching to the token, but when we'll send to ID2, we'll send the token and also its own certificate to make its identification and validation. Now ID2, when try to send to ID3, it will need to append the new payload here, so the token will getting bigger, and we'll also need to send the certificates here. So it now have 2 certificates from ID1 and ID2, and pass ahead, and ID3 do the same. So as you can see, we have a lot of information that's being sent here, but so it requires more bandwidth, but have some good points here, which are this model here allows offline validation. So this guy ID4, when receives the token and the certificates, it doesn't need to check with any identity provider or any kind of server or external server to validate this token. All the necessary information are here. We also can implement some anonymous mode here using all this model. We just need to, doesn't send the certificates here. And instead of putting, for example, SPIFFE ID as the audience, we can use just a public key of that workload. So in this way, we don't know who is the owner of that workload, of that public key. So we don't have the identification, but we know how to validate, and we have ways to validate that token. And so we have not difficult to implement anonymous mode using this model here. So as I said, we need a lot of or more bandwidth comparing with the other anonymous solution. So one of the possibilities that we have been discussing but not have a final solution is maybe creating some new documents, as we are calling lightweight SVID, which basically is what's essential to be in the certificate to identify and validate the workloads. So the idea here is to reduce the SVID just to the necessary information to perform this kind of thing here. And then as each byte counts, so if you can reduce some bytes here, it could be interesting because it gets bigger and bigger when we accumulate this and work through the path. So this could be very useful in this scenario. Okay, so we have another possibility, which is the anonymous mode. It's Schnorr concatenated that is using EDDSA instead of ECDSA. We are calling this like Choco biscuits because it's a solution which is based on biscuit solution. Biscuit solution, just to understand, is a token model that was developed by Clever Cloud. And we will see in details in the next slide how it works. But in our scenario, we used Biscuit-based solution, but we had some improvements that results in smaller token and faster validation. Here we are using something that's based on Galindo Garcia work. Galindo Garcia proved that Schnorr signatures can be concatenated. So in its work, it aggregates 2 signatures and use just one validation to validate both signatures. It's not aggregated, but it's concatenated. It's similar and it works pretty well and have faster validation. And what we have done here is to take this work here that aggregate that concatenate 2 signatures and generalize to be able to concatenate any number of signatures and use this model to validate. So we create a cryptographic linked signatures, and that's interesting because we are tying each hop with the previous one. But the point here is until now, we just have the anonymous mode that we have developed. So as possibilities here to make probably a better model is to study the state of art of aggregated signatures, because aggregated signatures will be even better results when comparing with concatenated model. But this could be a little tricky because in Biscuits, they just dropped the possibility about using aggregated signatures due to complexity and other difficulties of auditing. So but the things evolve, so maybe the actual state of art allows a simpler implementation. So we can study and see if it is possible here. So this is our main scenario. So as you can see here, in this model, we don't have the certificates being passed. And if you pay attention, this key resulting here is much bigger than this one, just to represent that the tokens here in this scenario are also smaller. And we will see how we can achieve these results. So talking just briefly about Biscuits, what Biscuits does is basically when you need to create an assertion, which is our block 0 here, you have your payload, which is this data. And before signing this, you need to create a key pair. And when create this key pair, you will sign not just your payload, but also the public key that you have generated, because this public key is related to the private key that the next workload will have to use to append information. So you create this, pass the assertion, and pass also this private key to the next workload. And we'll got something like this. This next workload, when appending information, will use the previously generated key and then can discard this. But to sign, you will need to generate another key pair and put inside the assertion. So basically, when you validate this, you take the public key from the first assertion and use to validate the next one, and take the second one to the third one, and this is go on until the last part. So here we need to make many validations as many parts we have, but it still works pretty well. But seeing that we thought about, so how can we improve, and we proposed something like this. In our scenario, we still generate this first assertion like we have done before. We generate our payload and sign this. But in this model here, we don't need anymore to generate a new key pair at each step. We just generate the signature, and just see that in the signature, we have 2 parts, R and S. And the secret here is that we will use part of the signature as private key. So when I append a new assertion to this existing one, I will remove this S part from the signature and use as the private key of my new signature. So the previous signature will be now just the R part, and my signature is still complete. So the idea is when you receive the token, when the workload receives the token, as a complete signature allow this workload to append information. But this workload cannot change the previous assertions because it doesn't have the S part anymore. It doesn't have the private key anymore. So it just can append, but cannot change the previous one. And this kind of works pretty well because when we need to validate, We also have to do a single validation. Of course, is pretty much complex than a simple validation of one signature, as I will show in the next slides, but it keeps working pretty well and faster than any number of validations. So the first demonstration that I want to show to you guys is using the ID mode. So what we will do, we have some application here, which is similar to any cloud application. We have some components, a front end, some middle tiers here, which are representing the steps of since from the front end until the destination. And here in the target, we have a database that contains information from users. Spire here will be used to establish MTLS connections, to provide the necessary keys to sign the tokens, and also the certificates that are following the token. For example, a user connects here using OAuth token. This front end here establish MTLS connection with local identity provider and exchange this OAuth token by a new minted ECDSA assertion. This identity provider creates this assertion and sends to front end with the certificate here. And then front end will do the same before sending to another component here, middle tier. It will append assertions to this token and send to middle tier the new token and now the certificate from identity provider and from front end. And this will happen with all the components until the target's reached. And then here, this guy will separate each part of the token and use each of the certificates to validate those parts. So this is the ECDSA-SVID. Let me show here to you guys this working. So for example, in our test environment, I already have our components running. So the subject workload is my front end, is where I will connect. So let's see the logs of subject workload, because I will connect now and probably will have some interesting thing happening. So our application here is just an example. It's like any kind of application. When we click here, login, it will redirect me to Okta, and Okta will provide me an OAuth token. As I was recently connected, so it was in cache, so I already have my OAuth token here with subject. I have just a checkpoint here. It's not necessary in the point of view of application, but when I click here, what we will do basically is this kind of exchange here. I will send the token to the identity provider and I will receive the ECDSA assertion and the SVID from the identity provider. Let's see this happening. That's pretty fast. And let's see here. Let's open and understand what's happened. For example, here I have the OAuth token that we have just created, which is this one. And I send this to identity provider and receive this kind of thing here. This, let me show you guys. This is the token, this is the assertion that was generated. And here we have something that's called ID artifacts. Basically is the certificate of the guy who generated this token, my identity provider. Okay, this is from the subject point of view. This is what happened until now. Let's now try to check the balance using this token. And as we can see, it worked and I got just $5 here. But the main point here is what happened behind the hoof. Okay, so let's see now the logs from the target workload, which is our destination. Here we will have probably some interesting things that I want to show, that just from the beginning here. Here is the beginning of the call that target workload received. It received an assertion, which is the assertion that was created in that just first step that we just see. And each hop had added a new assertion. So if I print this assertion, I can see from which hop it has passed, basically from all these guys here. And then a lot of certificates was received, one for each workload here. So we have a lot of certificates. In our proof of concept scenario, we are using these certificates to retrieve the public keys. And then after all the public keys are collected, we are going to use that to validate each of the claims and each of the signatures that we have here in our token. Also, we are going to validate the issuer and audience link to check and to be sure that they match. So basically is what have been done here. All the steps here, all the parts of the token are getting validated until here. And when we reach here in the end, we have validated all the signature, and we can perform one more validation that is not really the scope of this work, but it's very interesting. Basically, the idea is, okay, all the assertions here are valid, but what grants to me that we really have an OAuth token and a valid OAuth token behind it, because the idea is to hide the OAuth token. We don't wanna pass it ahead, but I wanna know that it's a valid OAuth token. So basically what we do is to ask for the identity provider zero knowledge proof that guy have this OAuth token. We receive this proof and we validate the zero knowledge proof, and we can give more details, but doesn't have time enough here. But we validate the zero knowledge proof, and then we grant that all the assertions since the origin are valid, and the OAuth token that's behind that are also valid. So we can now retrieve the user data and return this. So this is the main idea. And if you see, the main assertion have informations about the workload, which is our front end, and informations about the user, which is behind that workload. And this is the model from the ID mode, where we know by which workloads have passed. So just to finish, I'm going to anonymous mode, because now I will run the same application, but now using the anonymous mode. I will start here this mode, and while it getting started, I will just show here what we are going to do. So here we are going to do the same flow, but now the assertions are not signed with ECDSA, are going to be signed using ECDSA Schnorr signatures. So user will bring its OAuth token here, and we will exchange this OAuth token by a Schnorr assertion. And then front end will append its new assertion, its new payload to existing one, using part of the previous signature as private key, as we saw that before. And then we'll pass ahead to middle tiers. They are going to do the same thing here, and then it will reach the target workload, which will use our Galindo Garcia validation to check if all the parts from that compose the token are valid, and then we can return the results. So here basically Spire is being used by the application to establish MTLS connections, but the keys and the certificates are not being used in this scenario. Let's see. Okay, the anonymous mode is already running. So if you can see here, let's just focus now on target workload logs, because it's the most interesting part here. So our destination is just waiting for the call. And let's do it again. Okay, let's log in. OAuth token being received. Now let's generate our assertion. And now let's access our user data. So a lot of things happen here. Let's see what's happening. So as the same way we received now a token, probably not clear here, but this token is much smaller than the previous one, because here we receive the token contains the public key from each step. And the idea is, let's go assertion by assertion, extracting the public key and making the necessary creations here, because we need to create the hash of each step in the end, we will use the Galindo-Garcia validation. We just do one time using all this information to grant that all the signatures that's inside the token is valid. So just to show here, that's the last signature of the token, the most recent. So it's a full signature because we don't use it, the S part, to sign it. But if you see the previous one, is just half of the size because we had used that S part should be here as private key to generate this one, as well as this one, So all the signatures are just half, just the R part, and the last one is complete. So anyone which received this token can use it to append new payloads here. And then we also extract here, after all these validations, we extract the main assertion and verify using zero knowledge proof to grant that we have an OAuth token valid behind these assertions. And then doing this, we can grant all the assertions, we can grant the OAuth token and access the data from the user that made the request. And that's it. I passed a little bit about the time. Sorry about that, guys. That was I bring today to show. As a future work, probably we will work in the lightweight SVID and trying to implement something with biscuits and also analyze the possibility of using protobuf, not only JSON model. And that's it. Thank you, everybody. And I'm here to answer your questions. Thank you.
Awesome. Thank you, Marco. Any questions here, folks? I think everyone's still trying to process their all the schemas. That was very interesting. Would you? I think would be great if you can share the presentation as well.
Sure. Of course, I will share in the Slack group.
Amazing. Any questions from their people joining virtual? All good. I don't see any questions in a chat, but yeah, I'm very excited about this work.
Yeah, quick question from my side. Just thank you, Marco, for presenting. Just to know if is this something that is only like a research, or is there like a specific use case for organizations that are trying to apply this?
Yeah, we are working together with HPA group. So actually, at this moment, we are in a researching phase, but probably there are a lot of use cases that we are discussing. Two of them, and the probably most useful at this moment, are the token tracing. But we have mapped some other use cases like for IoT devices and the localization and geographic situations. For example, to know if that request passed for some geographic localizations that could be useful in some scenarios where there are, for example, restrictions about by which country this could go or not. So we are working over these use cases, but not to any one specifically.
Got it. Looks like we got a question from Ryan in the Zoom chat.
Ryan, maybe you can read it.
Yep. So it says that one of the main challenges of authentication protocols based around asymmetric key digital signature generation and verification in a large microservices deployment, where there may be many services involved in a single front-end request and many proxies or load balancers between microservices, is the performance cost, which is usually on the order of milliseconds. Have you explored any alternative token formats that aim to solve these performance problems?
Yeah, thank you for the question. That's a great point that we had to work the performance because, well, there's as we have discussed, we always fall in the same point. There's no free lunch. So sometimes if you need, for example, if you compare the ID mode that we have with the anonymous mode, the ID mode we probably have more time to validate because it involves certificates and involve much more things. So the token size will also be bigger. So probably there is not a way to ease that all, but if depending of the use case, for example, if the anonymous mode is enough, it could be interesting to apply because it reduces the token size. As we can see, it used part of the signature, the existing signature as the private key, so the token size gets smaller. And also the Schnorr signatures are easier and faster to validate. So the idea is to use this kind of model, which is the anonymous model or the concatenated model, as possible as we can. So one of our study points here and the future work is to analyze if it's possible to use Schnorr with ECDSA, because then we probably can get some benefits from Spire infrastructure and apply also the concatenated solution in this model. So probably will be the best of both scenarios, but performance is a really difficult way to find a solution, best solution, but we are working on it.
Yeah, thanks for the talk, Marco. This is really interesting. This is some cutting edge stuff. And yeah, my question is kind of something that we wrestle with at Uber because we run a pretty large deployment. And as security people, like we want to turn on authentication everywhere, but then that has a cost and the user ends up seeing some effect of that eventually. So sometimes we need to have convincing arguments why authentication needs to be everywhere, and anything we can do to address these performance problems, I think will really pay off in the long run and will help different companies that are trying to weigh those business decisions of what comes first, priority, the security of a given request or the performance and like latency that the user sees. So yeah, thanks again for the research. This is awesome. Looking forward to seeing what else comes out in the space.
Yeah, thank you. Yeah, the problem here is that we have performance issues from the signing side and the validation side, because we need to balance if what is most important, to be fast signing or in the validation phase. So we need to balance everything pretty well and to adapt to the scenario of the application needs. But we are trying to make the middle term well for the most use case that we have, at least at this moment.
Amazing, thank you, Mark. When do you think we'll have it's working in Spire? Is it somewhere next year?
Well,
this year?
That's a good question. We are working on it. Well, I don't have a day or an idea here, but it's working pretty well. The team is fantastic, and we are probably bring news as soon as possible.
No, next.
We are working with Ivan, Andrew, and I also want to invite anyone who is interested to get in our Slack channel. That's the Slack channel just about this subject. So please go there. Let's take change some ideas and work on it.
So first half of 23.
I hope so.
All right, let's make it happen.
Yeah.
Awesome. Thank you so much.